Good morning, my YouTube viewers. Crystal here. I'm here this morning because I wanted to give you the solution to the Kaggle house prices advanced regression techniques competition question. Basically, I've been working on this for several months now, trying different solutions. And what I wanted to do is I wanted to show my most recent solution to you. I just put it into the computer, into the Kaggle website, and I got a .16064 score, which is not as good as the previous scores, but I was trying a new technique, and when I was trying a new technique, it caused my scores to really shoot up. You can see how my scores really shot up at one point. The first time I tried it out using linear regression, it was 1.134, and that was really poor. And but whenever I was using the Ensemble Method and I was combining 3 different techniques, I got the score down to 12913. But I really wanted to experiment with this one technique that I'm going to show you. And when I experimented with this one technique that I'm going to show you, I was able to, how it shot right up to 1.13490, and I was able to use various techniques to get it down to 0.16064. And this is what I would like to show you. So even though my score's not tops, it's better than a lot of scores. So I'll jump to my leaderboard, and you'll see I jumped to the leaderboard, and the highest score was 0.00044. That's the highest that anybody has done. And you can see it's not terrible. It's not terrible. It says it's not an improvement, but it's not terrible. And I could keep going, and you would find out that there are scores that are a lot worse than my score. So that's really why I wanted to show this to you. It's not the worst score in the world, even though it's not the best score in the world. So I just first thing I wanted to do is I wanted to read you the problem statement that's on the Kaggle website. And it says, ask a home buyer to decide their dream house, and they probably won't begin with the height of the basement ceiling or the proximity to an east-west railroad, but this playground competition's data set proves that much more influences price negotiations than the number of bedrooms or a white picket fence. With 79 explanatory variables describing almost every aspect of residential homes in Ames, Iowa, this competition challenges you to predict the final price of each home. And it says the Ames housing data set was compiled by Dean DeCock for use in data science education. It's an incredible alternative for data scientists looking for a modernized and expanded version of the often cited Boston housing data set. So what I might do is I might actually go through the Boston housing data set and compare this to the Boston housing data set. I have actually seen the Boston housing data set, and I don't think it's as elaborate as this data set. This is a very elaborate data set that the training file has 81 columns in it. It has a lot of information. So without further ado, I'm going to go ahead and go through my solution with you. And it's a good solution, and I'm sure that I could do some more work on it, like maybe fine-tune the parameters or take out some features, and that might actually improve improve my score, but I still had a score of around 90, which I don't think is a bad score. So the first thing I did was I imported my libraries, and you can see I imported my libraries, and you can see the version of the library that I had. The next thing I did was I imported my files. We had a test file, a sample submission, a train file, and a data description. I then loaded my data sets. So you can see your DF train, and you can see that it's a very big file. It goes on, it's actually 81 columns. Then I loaded my test set, and it's the same one. It has 80 columns. I suppose if I wanted to improve my score, I could drop columns, because I can see Alley is a good column to start with dropping, because it's got lots of NaN features. So I could go back and try to drop the Alley column and see if that improves my score. You can look at the train file. It's got loads and loads of columns, 81 to be exact. They're objects, integers, and floats. Same with the test file. It has 80 columns because it doesn't have a sale price. So we're checking the DF train again and the DF test again, and we described our target variable with the sales price is a bit skewed. And one of my programs that I have on Google Colab, there was a function that if you put it on logarithmic function, it'll move it over towards the center, but I didn't put it in the solution. We've got overall quality. We've got a box file on the overall quality. And as you can see, that as the quality of the house increases, the price increases as well. Wanted to check for null values. I had to use this program to check for null values, and the reason why is because there were so many columns, 81 to be exact, that it didn't show everything. Whenever I just did a DF total is null sum, it didn't show everything. I suppose I could have put the code in DF total is null sum, and it would have put it in there, but it didn't show everything. And because it didn't show everything, I had to put it on a data file and then put it on a head of 20. We did the same thing with the test file. And what this does is this shows you all of the columns that have missing values. So what we did was we filled up all the missing values. So you can see here that I filled all the missing values that were in the columns, and all of the missing values were filled with the mode function. So we filled up all of the training missing values, and we filled up all of the test missing values. And then some of the things that we just filled them with no or zero or none. And so you can see it right there. So instead of filling it with a mode, we filled it with the basement was none. Some others floats were 0. So at the end of that, we checked again for some more null values. We used train.isNull.sum, and that would just give you a plain 0 instead of giving you the columns, which is what I previously had done. So it says part of the column. Now what we had to do was we had to print off a list of columns that are objects. So you can see all of the objects that were columns that were objects. So we had to take all of these columns that were objects and we had to put them to a label encoder. And when we put those to the label encoder, that made them numeric values. And that is what the computer wants to see. The computer wants to see a numeric value. So everything that was in the previous, every column that was in the previous command got put into a label encoder, and we did the test file, and we also did the train file. So then after we did that, we defined our X, Y, and X test values. Y is your dftrain.sellPrice.values, and X is dftrain.drop sell price and ID, and X test is dftest drop ID and axis. We did the standard scaler, and I found out the standard scaler didn't work. I tried just using standard scaler, and that was what brought my score up to over 1. And then I was experimenting with other scalars, because there was something that just called scalar, and there was something called PCA, and I experimented with the scalars, and the scalars actually made my calculations worse, so I had to take the scalar off. We used train test split to split the training file into 4: X train, X val, Y train, and Y val. We wanted to check the shape of X train, X val, Y train, and Y val. So you can see we've got the shape there. Now we have 79 columns in the train file, because what you need is you need the same amount of columns in the train file as you do the test file. If you don't, it won't work, because that's just how the program works. Because when we define our model, which is what we're doing now, we used gradient boosting regressor. The model has to be the same for the train file and the test file. If the test file has a different amount of columns than the train file, then it just won't work. It'll go into error and it won't work. So we fit our train file to our training set to gradient boosting regressor, and we printed off our score, and we got a score of 99%, which is very good in my opinion. And so we predicted on the model, and you can see this is the prediction. It gave us an array of values, and we printed off the score as well. So the training file had 99%, and the validation file had 90%, which is still good, because they say that if your score is over 90%, then it's good. So it was still good. We printed the validation file into a data frame, and we put the actual value. The actual values were Y val, and the predicted values were Y pred, and you can see the difference between the two values. We predicted on the test file, and we called that final labels, and it came up with an array. And we put the final labels into a data frame that we called final result, and we put the final result into a file called submission.csv, and here is the result, which is about a 90% accuracy. It's not as good as the previous ensemble that I did, but I'm going to experiment a little bit with feature selection and see if I can improve my score by taking out some features. Because what had happened was, the first time that I did this house price sales, I didn't really know what I was doing, so I was having to go onto YouTube and look at other people's works. And one person, he did it solely on the basis of one variable, on an X and a Y variable. So Y was the sell price, and X was something else. It was like a greater living area or something like that. And so he based his solution only on one column out of 81. And I played with that and toyed with that using the lasso command to actually get it up to about a 1.14. And then I was looking at some work of some other people, and the other people, what they did was they split it up into categorical values and numerical values, and they did a lot of, programming to get it to work. And then I was improved the score a little bit. And then I was able to do the Ensemble Method, which was to use 3 models and combine the 3 models in the hopes that the 3 models would give it a better score. And I was able to get up to 0.12. But I wanted to try this solution out just to see how it worked out. And it did. After I used the correct model, which was a gradient boosting regressor, it did go up to 90% accuracy. But I'm going to experiment and see if I can delete some comments and get the accuracy up. Now, what I'm doing now is I'm making this notebook public. So if you want to go onto my account on Kaggle, then you can look at the notebook and see the work that I did. So that concludes this presentation on the Amy's House Prices. I was using a label encoder to encode all of the categorical comments, or all of the columns that were objects. And so I wanted to show that to you, to show you one way to solve this problem, and it gave me a 90% accuracy. So let me know what you think. Give me any comments that you have. Let me know what you think. I'm going to experiment a little bit to see if I can improve the accuracy by definitely taking out the alley column, since it had a lot of NaN values. And if you like my work, please like, subscribe, and share. If you want to make a donation to my PayPal account, it would be very much appreciated, because I don't have enough subscribers, and the only way I can make money on my account is to ask for donations. So thank you very much for watching this video, and I look forward to making the next one for you.